There are four fundamental forces at play in our universe. Electromagnetic force is my favorite one among them. Electricity, as we know it, is the result of this fundamental force of nature. We use electricity to power our homes and to make technological breakthroughs, but we cannot fathom the real power of electricity until we study it at high voltages. It transforms into this uncontrollable beast that is very unsettling in its behavior and its physics. At such high energies, it has the power to even split atoms. The first step to study high voltage electricity is to create a high voltage power source. It must be simple and safe to handle. Let me build one such power source, which, when handled carefully, can help throw some light into the world of high voltage physics. I salvaged most of the components used in this build from an old CRT television set, including the flyback transformer. The transistor was rated for 1500 volts between collector and base and 600 volts between the collector and emitter. So I thought that was more than sufficient for my build and never really thought of a replacement transistor. The flyback transformer was a Chinese make and I couldn't really find a reliable datasheet for it as the information available online was pretty sketchy. So I decided to find it out myself, and here is the actual circuit diagram which I drew. All it took was a multimeter and an inductance meter. By the way, I measured the resistance and inductance values and tabulated them so that I can create a model for simulating the circuit. However, I couldn't find a way to know the turns ratio, so the model is more or less reliable except the voltages in the simulation. I wanted to use the internal windings of the flyback instead of winding coils on the core, which, by the way, is what I find when I do a quick internet search. I couldn't agree with this idea, at least for my requirement, because the transformer was not designed to operate this way, and by using internal windings, I was able to get sufficiently high voltages at the secondary with a current consumption of just under 1 ampere, and the circuit was just moderately warm after prolonged usage. I thought this approach was more efficient that way. Resistor R1 and R2 form the potential divider that produces about 1.1 volt across R2 when powered by a 12 volt DC battery. Diodes D1 and D2 are to protect the transistor from getting damaged due to the negative voltage spikes. Coils between pin 1 and 4 serve as the primary winding, and coils between pin 7 and 8 forms the feedback winding, and it is connected to the base of the transistor. The secondary is isolated between the high voltage wire and the ground, which is pin number 9. Initially, when the power is switched on, the base of the transistor receives a positive voltage of about 1.1 volt from the potential divider across the 22 ohm resistor. This base voltage causes current to flow through the feedback winding and into the base of the transistor, which in turn switches the transistor on and it conducts current through the primary winding. Due to the large inductance of the primary winding, the voltage across the inductor rises gradually. Remember, the feedback winding and the primary winding are wound opposite to each other. Hence, the increasing voltage on the primary induces an increasing voltage on the feedback due to the electromagnetic induction, but in the opposite direction. As the primary voltage keeps increasing, the voltage at the base of the transistor goes in the negative direction, going below the VBE on voltage. Thus, the transistor turns off, causing the primary voltage to decrease steadily. Now, so does the base voltage, but in the opposite direction. Once it crosses the VBE on voltage, the transistor turns on and the oscillation sustains itself again and again. This induces a very high voltage across the secondary, which is in the order of several tens of kilovolts. You may please note that the negative voltage at the base emitter junction is clamped by the voltage drop across the diode D1, thereby protecting the base emitter junction from negative spikes. The transistor has a maximum base emitter voltage of about 7 volts, so any increase above that would damage it. So D1 is very essential for the safety of the transistor. These are the two waveforms with and without the diode D1 for your reference. You can see the difference yourself. Now, you may think, what does capacitor C1 do? The primary inductance and the capacitor C1 forms a parallel LC resonance circuit. I know it doesn't look that way if you see the circuit diagram. Rather, they look like they're in series, but no. The inductance of the primary winding and the capacitance of C1 are in fact AC coupled to form a parallel LC resonance circuit through the power supply. And the voltage across the capacitor is the same as that across the inductor but inverted if you consider the ground as a reference. Consider this simplified circuit. The transistor S1 is just a switch which turns on and off the current through the inductor L1 of the primary winding. C1 forms the capacitance between the collector emitter junction. Now, switch S1 is controlled by the feedback from the feedback winding, which is 180° out of phase from the primary. Thus, it forms a negative feedback. This controls the base voltage. The base is also driven by the 1.1 volts from the resistor divider. This drives the current through the base of the transistor, turning it on. So, the switch S1 is closed. Now, current I flows through L1 and voltage starts to build up across it like so. And the energy is getting stored in the magnetic field. By the way, if you want to know how a ferrite core transformer stores energy in the form of magnetic field, then please check out this link. When the feedback voltage pulls the transistor base low, the switch S1 is open and the current suddenly stops, but the energy stored inside the inductor needs to go somewhere, and so it is forced to maintain the current flow. Now, if you see the capacitor and the inductor, they are in parallel and they are AC coupled, forming a resonant circuit. The current is thus pushed into the capacitor, charging it. In the process, the inductor develops an opposite voltage across it, which pushes the current through. How long it takes to charge and at what frequency depends on the LC time constant, which you can change by adjusting the value of C1. The value of L1 is fixed for the primary. I have selected 2.2 nanofarad because that is what gave me the highest voltage at the primary. Mind you, if you increase C1, it may increase the width of the half cycle, but it also reduces the voltage across the primary. You may note that the voltage across the capacitor is the same as the inductor and can be given by the expression Vc is equal to Vl minus Vcc. Vcc is obviously the supply voltage, which is 12 volt in this case, and Vc is the voltage across the capacitor and Vl is the voltage across the inductor. This you can see clearly from the waveform also. If you look carefully, the whole setup works like a boost converter. That is why the primary voltage is higher than the 12 volt that supplies power to the circuit. In a sense, it is like how a pendulum works. You just push it by nudging it just at the right time and it starts to swing by itself, sometimes swinging way past the extremes by just using that small nudge. I know it was quite an exhausting explanation, but when I started to work on electronics and tried to understand it, I always wished if someone could explain the basic stuff and not just broadly on the subject. I spent a lot of time searching answers, making mistakes, breaking stuff, and then learning concepts. So, it has been my mindset and one of the reasons I started this channel that this may help someone out there who's interested to learn science and find all the information they need, even if that makes the presentation a bit lengthy and undoubtedly boring to most people. Besides, where's the fun in science if you don't get to understand what you're doing? Before building the circuit, I prototyped the design on a breadboard and powered it from a 12 volt bench power supply. Sure enough, the design worked and there were no explosions or magic smoke. Well, what can I say? Math never disappoints. The only disappointment was me. I made a stupid mistake. While I was experimenting with different supply voltages, I forgot the need for higher insulation resistance. In a moment of carelessness, the high voltage jumped across the terminals and found its way through to my power supply, killing it instantly. After spending a long time in homage to the power regulators and op-amps for the sacrifice, I was able to get the power supply back in operation. That's all the more reason for you to listen to the warnings and take adequate precautions while working with high voltages. The first step in the build was to drill appropriate holes on the PCB. I took extra care to insulate the secondary ground terminal adequately. This time with a high voltage rated wire and an epoxy glue as insulation so that it cannot jump tracks on the PCB. The next step was to solder the flyback transformer nice and clean. Then comes the transistor. I used 2 screws to fix the heatsink to the PCB. Though at 12 volt it was slightly warm, the transistor is expected to heat up at high input voltages. This time, I used a metal oxide varistor and a box type 300 volt capacitor in an attempt to bypass any high voltages that may find its way to the power supply. The capacitor C2 improves the AC coupling between the primary and C1. I also added a power on indicator using a LED, also a very rudimentary reverse voltage protection with the help of a fuse and a diode D3. With this particular transistor, theoretically, one should be able to drive the circuit with higher DC voltages to improve the arc length perhaps, given that the voltage across R2 is tweaked by adjusting the potential divider to not exceed the maximum base voltage using this formula. After so much hard work, it's finally time to test the circuit. Though it works well at 12 volt, I decided to test it at 24 volts and as soon as I switched on, the arcs began flying around. It's really amazing how unpredictable electricity becomes at super high voltages. At this point, air, which is normally a good insulator, just breaks down and starts conducting electricity, which is what you're witnessing right now. The dielectric strength of air is about 3 kV per millimeter, depending on a lot of factors like electrode shape, humidity, temperature, etc. But I'm going to oversimplify things here and say, based on the distance at which it begins flashover, the voltages here are conservatively upwards of at least 60 kilovolts, if not more. How cool is that? I mean, it's literally so hot in there that air breaks down, but you get my point, right? Well, if I slow things down a bit, you can see a lot of crazy stuff happening here. Like, for example, there's this purple glow around the electrodes, then there is this cracking noise when the arc strikes between electrodes, and there is this strong wind that is blowing outwards from the electrodes for some reason, which I can literally feel hitting on my hands. So, what's happening here? Let me try to explain it briefly. What's happening here is literally a subatomic thunderstorm. The purple or the violet glow you see here is called the corona discharge. No, not the stupid virus that's making our lives miserable, but corona as in the sun's outer atmosphere, something in that sense. You're actually witnessing the air getting ionized and electrons being ripped out of the atoms here. The crackling noise is due to the shock waves created by the gases expanding at supersonic speeds. Well, the wind is called ionic wind, which is actually charged ions getting thrown outwards. Like I told you, the world of high voltage physics is amazing. Now that we have our tiny power source to generate high voltages, I'll now try to come up with more experiments and thereby try to explain more such high voltage phenomenon in my future videos. I hope you are able to learn something new and useful today. If you feel the same way, please consider subscribing to my channel and please like my videos and share them with your friends. I'd like to hear what you think about them. Suggestions, constructive criticism are all welcome. Just keep it civil. Comment section is open. Feel free to voice your opinion. So, that's all for now. Remember, engineer, experiment, educate. Thank you guys.